discuss about the motion estimation techniques. Now, the basic concepts of motion estimation I have already mentioned in the last class when I had introduced the basic concepts behind the video coding. What we had discussed last time is that if we have to encode a frame and we would like to exploit the temporal redundancy in order to achieve significant amount of compression. In that case, what we do is that if we take our candidate frame to be the frame number k, let us say some frame numbered k, which is the candidate frame. In that case, the candidate frame k could be encoded by one of the past frame, by using one of the past frames. Let us say the immediate past frame. Okay. And that immediate past frame we should be designated as I mean that should be designated as k minus 1. So, k minus 1th frame, which is used as the reference, is going to predict what frame number k is going to be. So, after finding out the motion vectors, it will apply the motion vectors onto this reference frame and predict k, and the difference between the incoming frame k and the predicted frame k, that difference has to be encoded. That is what we said. So, basically what we have is that a past frame, okay, what we are using as a reference is a past frame, and on the past frame, on the basis of past frame, we are predicting what the future is, right. So, basically it is, I mean, whenever it is estimating the motion, it is going back in time, okay, in order to find out the motion vectors, and when it is a question of compensation, that means to say predicting what it is going to be, in that case the prediction is going to be a forward prediction, right. So, whenever we are using a past frame as a reference, then it leads to a forward prediction. So, you can say that the process what we have described basically means that there is a backward motion estimation. Why backward? Because we are going back in time, okay. We are considering the past frame for motion estimation. So, we are calling that as the backward motion estimation, and whenever we are using backward motion estimation, it leads to forward prediction or forward motion compensation, whatever way you would like to call. Now, we can put the concept in the opposite way also, okay. Although it would look very puzzling, but let us say that why do we use a past frame for a reference, why do not we use a future frame as a reference, okay. Looks little awkward, because if we are going to encode frame k now, okay, in that case what I have just now suggested, that we should be using some future frame as a reference. Let us say the next future frame. The next future frame would be k plus 1th frame. So, k plus 1th frame we are going to use as reference, and with respect to that we are going to predict k. Looks little awkward, because we have not yet received the future frame. The frame k is as if like our incoming frame k, and then we are going to predict frame k on the basis of something which is in the future, which has not come yet. Okay, I mean, although the concept looks somewhat puzzling, but let us say that if at this moment of time some frame is going to be encoded, it does not necessarily mean that that is the coming that is the incoming frame coming out of the real time source. Okay. What I mean to say is that at this moment of time, okay, while the camera may be capturing frame k plus n, let us say, I can encode frame k. That means to say that I am only introducing some kind of a delay. So, what we can do is to have a prior storage of the frames. So, if we have some prior storage of frames, in this case let us say that if n frames are kept stored, and while frame k plus n is being processed by the camera, while frame k plus n is being captured by the camera, we have frame number k already available in the memory, okay, for encoding. So, what we are going to do is that frame k is there in the memory, frame k plus 1, that is also there in the memory. So, in such case it is possible that we can predict the frame number k by using some frames beyond k as a reference. So, k could be the frame to be encoded, we can still call that as current frame, no problem. As far as the encoding is concerned, it is the current frame to be encoded. Maybe that with respect to camera it is delayed, but frame k, the encoder treats frame k as a current frame and k plus 1 as a reference frame, which is a future reference frame, but that is also stored in the memory. So, now what we are going to do is that we are again going to predict the motion. So, what we are going to do is that in a very similar manner, what we are going to do is to subdivide the frame k into a number of non overlapping blocks, and for each of these blocks we are going to find out the motion vector that would come out of the motion estimation with frame k plus 1 as the reference. Okay. So, in this case what we are doing is that we are using the future frame as a reference. With respect to frame k, we are using future frame as a reference. So, which means to say that the prediction that it is doing is for a frame which is older. So, which means to say that this is a backward prediction. This is a backward prediction, and the motion estimation process in this case is a forward motion estimation. Why? Because frame k is the candidate frame and it is finding out the motion vector by considering frame k plus 1, which is forward in time. So, it is a forward motion estimation, or that leads to a backward prediction. Okay. So, the first case, the case what we discussed earlier, that was a forward prediction, and what I have described just now is the case of backward prediction. Now, why is forward prediction required? When is forward prediction required? When is backward prediction required? You see, what we are doing is that we are dealing with moving objects. Let us say that we draw 3 frames. So, there is frame k, there is frame k plus 1, there is also frame k minus 1. Okay. We have got 3 frames, and let us say that there is some object, let us say this is the object, okay, which is at some position in frame k minus 1. Now, in frame k plus k, it has moved by some extent, some motion vector is there. So, by that it has moved, and in the frame k plus 1 it has moved further. So, let us say that it has come to this position. So, what you can clearly see that in frame k plus 1, the part of the object boundary maybe would have been like this. So, the part of the object boundary lies outside the frame. So, it is not visible to us. What is visible to us is only what we have within this rectangular box. So, this is beyond the frame size. So, there is some amount of occlusion which has taken place, means that this part of the object which was visible in frame k minus 1 and which is visible in frame k is not visible in frame k plus 1. The opposite also could have happened, like I might have got some object like this in frame k minus 1, and then in frame k plus 1 the object may be like this, in frame k the object may be like this, and in frame k plus 1 the object may be like this. So, in this case what is happening is that this object is partly occluded in frame k minus 1, but it is unoccluded in frame k and frame k plus 1. So, how the object moves is not something that we can really tell about it, because these are physical objects. So, they may move, they may be out of screen and slowly come into the screen, or they may be inside the screen and go out of the screen. Okay. Either of these two cases can happen. So, when we have some occlusion, let us say that when this is the scenario, in that case we cannot have any prediction for this region of the object. Why? Because simply this region is not available in the previous frame. Okay. Whereas, in this case, if we do some forward prediction, okay, the forward prediction or the backward motion estimation would be problematic, because in this case we have only part of this object. So, we will not be having any part like this which is not visible. Okay, those parts will not have any correspondence in the previous frame. So, the best combination could be that if we employ, I mean, since we are having the idea of storing the frame in the memory and then use it for encoding, in that case we should be able to use both past frame as well as the future frame, okay, for our motion prediction. Okay. We can use both the past and the present for prediction, and in that case what we are doing is that we are employing both forward prediction and backward prediction. Now, when we are using both forward as well as backward prediction, okay, then forward and backward prediction combination, that leads to a bidirectional prediction. Now, why should people use bidirectional prediction? The reason behind this is that, of course, whenever you are having two reference frames, if you commit any mistake in estimating the motion with respect to the past frame, maybe the same amount of mistake you are not going to have for having the while having the backward motion prediction. If you have error in forward prediction, you may not have the similar error in backward prediction, or vice versa. So, there is always something, I mean, averaging always gives you a better estimate, okay, because one estimate could be wrong and that may be corrected by another estimate. And not only that, the question of the occlusion also could be there, that some object may be occluded in the past frame, some object may be occluded in the future frame, but whenever you are using both forward and backward prediction, in that case you can decide that whether to take forward as the reference, or whether to use the backward as the reference, or whether to use both as the reference. So, bidirectional prediction also could be employed. Now, this leads to some important concept about the picture encoding. Picture means that video frames, I mean to say that when the video frames are continuously arriving, one can have a forward prediction, one can have a backward prediction, one can have a bidirectional prediction. Okay. Now, in the video coding standards, all these mechanisms are employed, but before I go into the aspect of forward and the backward predictions, okay, and using it in the encoding of the frames, let us address a very fundamental question. Let us say that a video sequence is starting. Okay. So, we have started a video sequence, we have started encoding a video sequence, and we have the first frame to be encoded. Now, the first frame does not have any past reference. Okay. So, what should be our starting point? We do not have any past reference, and because we do not have any past reference, there is no frame that has been stored also. Okay. It is just coming for the first time. We have obtained the first frame from the camera and we would like to encode it. Now, in absence of any reference, the only mechanism that we can adopt in order to encode the first frame is to treat the first frame just like a still image, right. So, just like the way we said while talking about the still image compression, that means to say that you can only exploit the spatial redundancy, you can adopt techniques like the DCT or the wavelet, okay, in order to encode the first frame. So, the first frame is not having any inter frame prediction. By inter, I mean to say that using another frame for prediction in between the frames. So, we are not using inter frame. So, I can only say that the first frame will be intra coded. So, the first frame in the video sequence, will be intra coded, right. Subsequent to the first frame, we do not have problems, because when the second frame comes, I can use the first frame as the past reference, okay. And then if I store the second frame, okay, and then the third frame is the incoming frame, or rather to say that second frame has come, I have stored it, third frame has come, I have stored it, fourth frame is coming, and I would like to encode the second frame. In that case, I can use for the second frame, I can use the first frame as a reference, I can use the third frame as a reference. Now, it is not essential that the prediction will be done only by one frame forward or one frame backward. Prediction by one frame is only as an example that I said, but you can predict what is going to be 3 frames ahead or 5 frames ahead, or you can predict with respect to what was 3 frames behind, 4 frames behind, 5 frames behind, like that. So, so when k is the candidate frame, we can have k plus n as a reference, we can use k minus n as a reference, okay, where n is a quantity which could be an integer greater than 0. So, in such case, so all subsequent frames would be intercoded, all subsequent frames will be intercoded. Now, whenever we are doing inter-frame coding, in that case one can use forward prediction or backward prediction or bidirectional prediction. So, whenever it is forward predicted, in that case means using the past reference, forward predicted frames are referred to as P frames. Intra coded frames are referred to as I frames, okay. And if we are doing bidirectional prediction, so if the frame is bidirectionally predicted, then we are going to call it as B frames. So, we have I frames, P frames and B frames which are present in the video sequence. Now, what is the ordering that one has to follow? See, the first frame in a sequence, okay, has to be an I frame, right. Now, let us say that we can use this I frame in order to predict few frames ahead. Let us say second, third, fourth, fifth. Fifth frame we are having a forward prediction. That means to say that whenever I am encoding the fifth frame, I already have the first frame stored in the memory. So, by comparing the fifth frame with the first frame, I can obtain that what the motion vector is going to be, and I can apply a forward motion prediction on the frame number 1 to predict what frame number 5 is going to be. So, frame number 5 would be a P frame. So, this is frame number 1, this is frame number 5, which is a P frame. Now, interestingly, I have not yet encoded frame number 2, 3 and 4, which are sandwiched in between frame number 1 and frame number 5. Now, after predicting frame number 5. Okay. What we can do is that we can use both frame number 1 and frame number 5 as the reference. If we have to encode a frame in between, let us say frame number 2, when I have to encode frame number 2, I can use 1 as the reference, I can use 5 as the reference. So, which means to say that I can have a bidirectional prediction. Okay. Also for frame number 3 and 4, one can adopt bidirectional prediction. So, frame 2, 3 and 4 have to be bidirectionally predicted. So, I have a I frame, I have a P frame here, and in between the I frame and the P frame, I have 3 B frames which are sandwiched in between. 3 is just an example, it could have been 2 B frames, it could have been 4 B frames, anything like that. Now, because 5th frame is available, okay, now I can predict by a very similar mechanism, I can predict what frame number 9 is going to be. So, frame number 9 could be used as a P frame, and because I have both 5 and 9, okay, it is possible to bidirectionally predict frame 6, frame 7 and frame 8. So, that all these frames 6, 7 and 8 would be the B frames. Okay. So, this is the sequence in which the frames are getting encoded: I, B, 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 P, again B, 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 P, like that. This is the sequence in which, so this is the total scenario that we would like to encode frame 1 as I, 2 as B, 3 as B, 4 as B, 5 as P again, 6 as B, 7 as B, like that. But whenever we are encoding not in the correct order, because first we have to encode frame number 1, then we have to encode frame number 5, and only when 1 and 5 are encoded, it is possible for me to encode 2, 3 and 4, and then I have to encode 9, and only when both 5 and 9 are encoded, I can encode 6, 7 and 8. So, there is a juggling in the ordering of the encoding that is being done, and that has to be there if we want this prediction to be done like this. Now, what is the advantage in having a prediction like this? You see, first frame is definitely without any past reference. So, in absence of any temporal redundancy, it is quite expected that we are consuming a large number of bits in order to encode. So, if we have, let us say that for a part of the video, if I have this many this much as my available bit budget, okay, then it is possible that I use a bulk of it for encoding the I frame. Bulk of my bit budget would be encoded for I frame. Let us say that I encode up to frame number 13, let us say. From frame number 1 to frame number 13 I encode. So, I frame would contain the maximum number of bits, will consume maximum number of bits, and followed by I, the P frames would consume some amount of bits, but definitely significantly less as compared to the I frames. But the B frames would consume very little bits, okay, because as you can see that number of B frames are much more than the number of P frames or the number of I frames. So, the B frames would consume much less bits, okay. So, only this much, whereas P takes this much, 4 P frames takes this much, and 1 I frame could be taking this much. This is just a fictitious example that, I mean, this is the way it is. So, that means to say that we would like to have very few I frames, okay. I have so far considered that only the first frame is an I frame, okay, and we should have as many B frames as possible. But let us have a look at some practical consideration. The practical consideration is that whenever we are having, whenever we are estimating the motion, Okay. Then we are making some prediction error, okay. And of course, we are not terribly worried about making prediction error, because as I said that the prediction error would be encoded, the differential which is the prediction error, that will be encoded by exploiting the spatial redundancy, and that information goes into the channel. So, that I mean decoder not only gets the motion vectors, but decoder also gets what the prediction error is going to be, and then the reconstruction could be done. So, some amount of error we are not terribly worried, but whenever we are using, okay, to begin with there may not be a problem that frame 1 to frame 2 we make some prediction error. Now, frame 3 would be predicted by frame 2, okay, or frame 4 would be predicted by, I mean whatever, I mean as we proceed in time, okay, then our sanctity of the reference, that also degrades. Like say for example, between frame number 1 and 5 I have used I frame and P frame as reference and I generated these B's, but between frame 5 and 9 I take 5 and 9 as reference and I generated these B's. Now, would these 3 B's be better or these 3 B's be better? Definitely these 3 B's. Why I am telling this? Because here this is the I frame. So, this is without any prediction error. Now, when I am predicting frame number 9, by now I have accumulated some amount of prediction error. So, the sanctity of my reference has degraded, and if my reference itself is not having the proper sanctity, in that case the in between sandwiched frame that I am generating by treating the frame number 5 and 9 as reference, that also will have some amount of error. So, if we proceed in this manner, it is possible that after sufficient time has elapsed, let us say that after 100 frames, okay, we may find that our prediction is awfully bad, especially whenever we are having rapidly moving objects. Okay. So, in such kind of cases what we should do? In such cases the mechanism that is employed is that we should forcibly, I mean after some predetermined time, we should forcibly introduce some I frame, because okay, just to ensure that the predictor that the prediction error does not accumulate beyond some stage. Okay. So, that is the reason why we introduce some I frames forcibly. So, this is called as the forced updating, okay. And in such kind of case, so what we can have is that we can divide the picture structure as a group of frames, okay, where divide the video in a structure like this, that we can form a structure which we can call as a group of frames or group of pictures, because group of pictures is a terminology that the standard makers use. So, it is called as the GOP. So, one GOP configuration, so one particular GOP may have a bit distribution like this. Okay. Now, one GOP would be followed by the next GOP. What I mean to say is that if let us say that I take that a GOP consists of 13 frames. So, n is equal to 13. So, when the 14th frame comes, again the next GOP starts and the next group of pictures start with another I frame. Okay. So, I explained to you the concept behind the I frame, P frame and B frame, and this terminologies have been used in the video coding standards. I will come to the discussion of the video coding standards very shortly, okay, within next 1 or 2 classes only. But before that, what I wanted to say a bit about it is that how this motion estimation is being done. We have been talking about motion estimation, okay, but the motion estimation is a simple issue, no doubt, but extremely computationally involved issue. So, let us see that how we do the motion estimation, what is the computational complexity that is involved, and how we can attempt to reduce the computational complexity without having significant degradation in the prediction performance. So, again go back to the discussion that we had in the earlier class. Okay. What we are going to do in the case of motion estimation is that we must define a search space over which a candidate block has to be searched. So, we must search for a candidate block, and then we must try to find out whether the candidate block, okay, matches with that position in the reference block. Okay. So, that means to say that we must have a matching measure. Okay. So, we must have a matching criteria. Now, what type of motion estimation are we going to employ? I had said in the last class that we are going to adopt a backward, I mean we are going to have a block based motion estimation. So, we are going to subdivide the image into a number of non overlapping blocks, and we are going to estimate the motion for every such non overlapping block. So, it is a block based motion estimation, and the matching criterion which are used are as follows. So, the matching criteria for block based motion estimation that is, one is the mean of squared error, or what is called as the MSE, mean of squared error, then mean of absolute difference, this is referred to as MAD, mean of absolute difference, and then another criterion that is used is matching pixel count. Or also referred to as the MPC. Now, in the MSE or the mean squared error criterion, what we are going to do is that we are using some reference frame. Let us say that the reference frame is a past reference frame. It does not matter whether it is past reference or future reference, because we will just change the index accordingly. But what I mean to say is that supposing we take S n1 n2 k. So, k is the current frame. So, k is the index for the current frame, okay. And for the reference frame we are considering the intensity function as S n1 n2 k minus L. Okay. And if we have L as greater than 0, in that case this is a past frame, and past frame is used as a reference, let us say. Now, what we are going to do is something like this, that let us say that this is the image, okay, and this is a particular candidate block position. This is the coordinate position of a candidate block. Let us say that the centroid of this candidate block, or the center position of this candidate block, is lying over here, and we would like to search that in the past frame where this block was. So, we define a search window. Okay. Now, realistically speaking, although one can consider that that block may move anywhere in the past reference frame, but again considering that there is a that it is a physical object, and the difference between the difference in time between the present frame and the past frame is only a matter of 30 milliseconds or so, okay, if we are considering a 30 frames per second rate for the video capture, then every physical object is going to have some restriction about the object motion. So, whenever we are considering the search window, let us say that this is the search position, okay, then then there is a particular range over which we should search. There is no point in searching everywhere. So, we define a search range, and let us say that the search range, okay, is plus minus w number of pixels. So, what I mean to say by plus minus w is that if this is the current frame position, current block position, we should search within a space of this, okay, where this goes as minus w to plus w horizontally, and again minus w to plus w vertically, okay, taking this to be the 0 0 as the reference. Okay. So, total number of search positions is how many? Total number of search positions will be, yes, 2 w plus 1 by 2 w plus 1. And why plus 1? Because this center position is also a position to be searched. So, 2 w plus 1 into 2 w plus 1, this is the number of search positions. So, this is actually going to decide about our search complexity, okay, 2 w plus 1 into 2 w plus 1. So, we should have less value for w. So, which means to say that when I have w as plus minus 7 pixels, okay, or rather w as 7. So, the search range is plus minus 7 pixels, then the total number of search positions becomes 225. So, 7 is not a large number, but 225 search positions is definitely a large number. 7, I mean going to the left in 7 pixel, going to the right in 7 pixel, going up by 7 pixel, going down by 7 pixel is quite feasible as far as the realistic motion is concerned, but searching for 225 such positions is really difficult. But let us say that we have a very good computer, okay, which can compute the motion in real time, okay, because again mind you, the motion estimation has to be done in real time. You have got only 33 milliseconds at your disposal. I mean, whenever you are having a frame rate of 30 frames per second, okay, you have only 33 milliseconds per frame at your disposal to encode the frame. So, if you employ a very slow processor, okay, or because of having so much of search complexity, if you cannot complete your frame encoding within 33 milliseconds of time, in that case you are definitely going to lose the real time effect. You have to then skip some frames, I mean you have to lose information, all sort of problems would arise because of that. So, what I mean to say is that let us restrict. So, for 30 frames per second rate, once we are considering that, then we should have a real time computation, and real time computation means the computational load should be really considered very carefully. Now, what is the computational load? Now, in order to compute the matching criteria based on the mean square error, what we do is that the mean square error measure, okay, let us say MSE, if we are, let us say that we are computing the matching score with a displacement vector of I j. So, I j is the displacement vector. Now, I j will vary because in the case of search, what we are going to do is that we are first going to place this window at this position, then shift it to the next pixel, then shift it to the next pixel, like this we search everywhere. So, that means to say that we have a current displacement that is applied. If I and j both are 0 0, that means to say that we are searching only at the center position. If I make I is equal to plus 1 and j is equal to 0, this means to say that I have only proceeded in the n1 direction by one step, and in the n2 direction I have not given any extra displacement. So, the mean square error at the ij displacement position should be indicated as this, that we use the two indices n1 and n2 and define it like this. N1 summation n1 is equal to 0 to n minus 1, n2 is equal to 0 to n minus 1, s n1 n2 k minus s n1 plus I. Why n1 plus I? Because I have taken ij to be the displacement vector. So, in the reference frame I will go to the position n1 plus 1, n2 plus j, and the reference frame is the past frame. So, I consider k minus L with L greater than 0. So, this is the difference in the intensity at the corresponding position, because n1 n2 is considered to be displaced at n1 plus I, n2 plus j. So, this is the difference in the intensity, but we do not deal with the difference in intensity, because the difference in intensity could be positive or negative. So, if we sum up the difference in intensity over a block of pixels or over the pixels within the block, then we may be baffled by a number 0 saying that, as if to say that there is no error, but really speaking it may be just a compensation of the positive errors and negative errors. So, errors should be always represented as positive. So, to do that we do a squaring of this. So, but we are saying it as mean square error. So, what we have done is to sum up this error squared or the squared error over the entire window. So, in this case we have assumed n by n, capital N by n to be our block size. Again, just like the way we used for the transforms, we had used n is equal to 8. Similarly, one can use n is equal to 8 as the block size, although in the recent standards, I mean, people have been using variable block sizes. So, n has come down to 4, or n could be increased to 16. So, we can have a search over 4 by 4, as small as 4 by 4 or as large as 16 by 16. Now, so that means to say that if n is equal to 8, in that case this summation computation would involve 64 additions, n square number of additions, right, and this is mean square error. So, we must divide the whole quantity by 1 upon n square. So, the mean square error definition is this. Now, this is at a particular displacement vector position I j, but I must change this displacement vector while searching. I must change this displacement vector, okay, so that it spans the entire search window, okay. And by exploring several such values of I and j, which value I should consider? I should consider that value where the mean square error happens to be the minimum. Okay. So, to do that, what we do is that we consider d1 and d2 to be the displacement vector, or rather to say d1 and d2 to be the motion vector. So, this is the estimated motion vector, and how the motion vector is defined? We must find out the minimum value of the MAC ij, but the minimum mean square error value is not important. What is important to us is the position at which the minimum occurs. Now, the ij position for which the minimum occurs, that should be my d1 d2 value. Okay. So, when I take this function, when I take the minimum of this function, in that case the minimum must be computed over I and j, but I and j happens to be the argument of this mean square error. So, I should search for the argument that leads to the minimum value. Okay. So, d1 d2 should be defined as the argument minimum over ij MSE ij. So, this is the way by which we can compute the mean square error. Now, you can realize one difficulty in this process, that we have not only 64 additions, but 64 number of squarings are also involved, because there is a square term in this MSE computation. So, 64 squarings are to be done, or 64 multiplications, and multiplication is of course a very costly resource. If you are doing multiplication in software, you are going to take enormous amount of time. If we are using hardware multiplier within the chip and all these things, in that case the hardware is going to be very costly. So, in order to have a measure that does not use this, does not involve this squaring, in that case a very similar idea can be employed, but instead of taking the square, you can take the absolute difference in the intensity. So, that also would ensure that the sum total or the individual difference values would be positive, and the sum total also will be some positive error. So, that is actually used in the minimum of absolute difference criteria. So, minimum of absolute difference criteria, what I have mentioned, minimum of absolute difference or mean of absolute difference and taking the minimum of that. So, that is the MAD measure, and the MAD measure is defined like this, that MAD at the position ij would be given as 1 upon n square summation n1 is equal to 0 to capital N minus 1, n2 is equal to 0 to capital N minus 1, and in this case I take the mod S n1 n2 k minus S n1 plus I n2 plus j k minus L mod of this. So, this is the MAD criterion. Okay. Matching pixel count is another measure. I need not have to elaborate the MPC, because MAD is something which is most commonly employed in most of the almost all the standard implementations which you will find reported in the literature, or even in the standards. What they recommend is to compute the MAD, because the advantage here is that you are computing the difference, but you do not require any multiplications, you do not require any squaring. So, all that you need is only the adder and subtractor. Using a subtractor, you just take the difference of this value, okay, take the absolute difference of that, and then you just add up the values. So, this will involve 64 additions and 64 subtractions. Okay. So, so till this much we learn in this class, and in the next class we will see that how efficiently the matching can be performed, okay, and also a bit idea about the video coding standards. Thank you.